ladies and gentlemen, this class recording has begun. So, first, the last 4 days we spent developing this picture. The last 4 days we spent developing this picture and then ultimately going through and assigning values to all those different orbitals, right, and everything like that. Can we agree that developing this picture and interpreting it was a pretty complex process?
Yes.
I think so, right? So, this, while complex, this is part of our unit on atomic theory, right? Theories explain things, yes? Part of our explanation of an atom and how it makes up all the pieces of matter that exist in our universe deals with the structure of that atom. And this represents the structure of an atom. Where are electrons in relation to the nucleus? And we found out that electrons are located in a place called orbitals. What was our definition of an orbital? Tim, go ahead. A place where electrons are most likely to be, right? And these shapes and these colors all represent likely areas where electrons are. Okay? Good there? Yeah. Now, using this diagram and the subsequent numbers that go along with it can get a little bit cumbersome, right? It's very detailed, but sometimes we don't need all this detail. Sometimes we just need a quick representation of what an atom or the structure of an atom is in relation to the electrons. So we come up with a shorthand way of representing this complexity. Okay? Good there? And that's where we're headed today. So we are going to start off and talk about orbital filling, which consists of orbital diagrams and electron configurations. Okay? That is where we are for the next couple days. Okay? Good there? All right. Yeah. So here's the relation we make going along with our analogy from last week. We said that quantum numbers are kind of like what? An address, right? An address for where electrons live, okay? And just like on your street, there's a bunch of addresses for a bunch of houses, okay? But as we discussed, just because you have an address, that doesn't mean that you're necessarily there, right? You're there a lot of times, but not always. And all those different addresses on your street, there's a different likelihood of finding people there. For example, any of you have neighbors that have like small kids, 2, 3 years old, maybe preschool, okay? If we went to that house on your street right now, 10:15 in the morning, are we likely to find people there? Little kids that okay. Let's say now if there's other places like places that have stay-at-home moms and little kids, right? We would be more likely to find people at a house that has little kids than we would be likely to find people at a house that has high schoolers and parents who work and go to school, yes. Right? Just like that, the addresses are all there, the houses are all there, but the likelihood of finding electrons depends on a couple of different factors, right? The likelihood of finding people depends on a couple of different factors. So's the case with our orbitals. The orbitals are all there, but which orbitals are filled and which orbitals aren't depends on a couple factors. Actually, it depends on one big factor, okay? So, relating back to an example, a demonstration that I did for you guys when we were first talking about Bohr's model of the atom. Why does this happen? Ready? Gravity is how it happens. Why does it happen?
You dropped it. You let go of it.
Kind of. Jason said because it felt like it. we give a name to that because it feels like it. What is the way that we cause change to happen? Energy, right? So, Stephen, why does this happen? Let's talk about it from an energy standpoint. Okay? Tara, go ahead. Because it wants to get rid of potential energy. Right? You said energy, right? Specifically energy. I didn't hear that part. All right. The ball falls because it has less energy on the ground, specifically gravitational potential, than it did up here in the air. Gravity is how it gets rid of that energy, but it falls because it has less energy down there than it does up here in the air. We said energy governs why things happen, especially that search for getting less energy, right? Over the past couple of days, we talked about quantum numbers and orbitals and stuff like that. And the first orbital that we drew was this one, right? The yellow sphere. And we said we could tell me two things, actually maybe three things about that orbital. What can you tell me about that orbital? Why was it the first one we drew? Devlin, what's one reason? Electrons have less energy in this orbital. That's why it's the first one we drew. Why do electrons have less energy in that orbital? Oh, it's closest to the nucleus, right? So it's close to the nucleus. It has less energy. But one more thing you can tell me about that orbital. One other thing we talked about with this orbital. It has less energy. It's close to the nucleus, but it's the only one, let's go with the first principal energy level, right? It's pretty small. And why is it small? Close to the nucleus, but why aren't there a lot of electrons there? Because they repel each other, right? So it's close to the nucleus, it has a low energy level, but there's not that many electrons there because we can only fit so many before they start repelling each other, right? These are all energy considerations, right? And that's what we're going to use to come up with a representation of where electrons actually are. Okay? So, the Aufbau principle is going to govern which orbitals actually get filled. So the Aufbau principle says orbitals are filled from lowest energy to highest energy. And we learned from Bohr and Bohr's model, even though it's not completely right, we did learn one thing about low energy orbitals and high energy orbitals. What did Bohr tell us about low energy versus high energy? Lauren, go ahead. High energy ones are farthest away from the nucleus, low energy ones are closest to the nucleus, right? So orbitals that are closest to the nucleus are going to get filled first because they have lower energy. Or electrons will have lower energy when they are in those orbitals. That was one thing Bohr did get right. Okay? His whole model wasn't correct, but he was right about this part. All right, good there? Okay. The next thing that shows up in your outline are these two charts, okay? So first, before you ask, these charts will be on your test, so you don't need to memorize them, okay? They are the same chart. Actually, they're not the same chart. They tell you the same information, just in two different ways. So whatever one you feel more comfortable with is fine. I like the one on the left better, and that's the one I'm going to reference during class, okay? All right, so let's take a look at the one on the left. Along the left outside edge of the drawing, what does it say? Along the left outside edge, what does it say? Increasing energy of electrons in orbitals. And there's an arrow that points which way? Up. Meaning, which way are we going to read this chart? So we're going to start at the bottom and go up, because we want to start with things that are low energy. Okay? Good there? All right, let's talk about what we're going to do with this. We are going to make something that is called an orbital diagram. Okay? That picture we spent the last 4 days developing is a diagram of orbitals. But an orbital diagram is a simplified version of that. An orbital diagram shows the distributions of electrons within an orbital. Or within orbitals, I should say. I'm sorry. Orbital diagrams show the distribution of electrons within orbitals. And that means we have to have something that represents our orbitals. Depending on what book you read, what information you go to, what website you go to, whatever, we can see different versions of orbital diagrams. They all tell the same information, they just look a little different. So sometimes you'll see circles, sometimes you'll see lines, sometimes you'll see boxes to represent orbitals. But you will always see arrows to represent electrons. So they can look a couple of different ways, right? Got these circles that have some arrows in them. We got these lines here with some arrows above them. Sometimes you'll see boxes with arrows inside of them. They're all showing the same thing. Okay? So this, putting together some combination of these things, is how we make an orbital diagram. Yes, Lauren? That's why I changed the wording on the quiz, right? Because, like I said, an orbital diagram is a representation of that big picture that we spent the last 4 days making. All right? I realized that you guys didn't see this yet, and that's why I was like, I had to tell you, ask the question in a different way, right? That's why I said that one that was circled was, actually here, I'll pull it back up, right? Okay. So here, right, S orbital in the third principal energy level, right? Okay, Jules, plug your ears. No. So, that it's in the third principal energy level, what does that tell you about N? N has to be what? 3. So that gets rid of choice B, because N is equal to 2, right? And then, if it's in an S orbital, right, what does the L value have to be? 0. This is the only one that has N3 and L0, all right? Okay. All right. So, let's start off. Okay? And down at the bottom of your outline, it asks you to draw an orbital diagram for hydrogen. Okay? So, going back to our definition, right? An orbital diagram shows the distribution of electrons within orbitals. So before we draw an orbital diagram for a specific atom, we need to know how many electrons we have to show. Okay? For this case, we have to show 1. Why, Devlin? So we go to the periodic table, and we find that hydrogen's atomic number is 1. Right? Yes, no, maybe.
Yes.
Okay? Technically, the atomic number tells us what about an atom? How many protons it has. But it also, by default, tells us how many electrons as well. Okay? So, we know that we have to show 1 electron. This 1 electron is going to go to the orbital that has the least amount of energy. Right? So, where are we going to go to find out which orbital has the least amount of energy? Well, yes. Right? Okay. We're going to go to this chart right here. Okay? And we said we're going to read this chart from where to where?
Bottom to top.
So we start at the bottom, right? And we go up, and the first orbital that we come across is what?
1s.
1s, right? So, the fact that it is a 1s orbital, you could tell me 2 things about it. The fact that I called it one, or that we call it 1s, you should be able to tell me two things about it. L equals 0. Okay, that's actually not one of the things I was thinking, but that's true. Cheyenne, what were you going to say something? L equals 0. Okay, tell me something about the orbital itself. Say again? It has low energy because it's where? Close to the nucleus. That's the one part, right? The fact that it's an s orbital. What should you be able to tell me about it? Maddie, go ahead. It's a sphere, right? So a 1s orbital is close to the nucleus and it's a sphere, okay? While those things are true, this diagram is meant to simplify all of those things. So instead of drawing that big elaborate picture of all those different shapes and colors, we simplify it. We represent the 1s orbital. I like to draw lines just because it's less things to draw. So I draw this line, and underneath it, I label that line as 1s. That's representing my 1s orbital. Now, because of what we talked about over the past couple of days, you should be able to tell me it's close to the nucleus, it's in a sphere, but this is how we represent it. And then we said that how do we represent the electrons that are in those orbitals? Why don't you look like 3 lines above where we're drawing on your paper? An arrow, okay? So, here, you'll see as we go along, there's a reason for this. And on your paper, and when I draw it up here, I usually draw a one-headed arrow, okay? Just because it saves time when we have to draw a bunch of them, okay? This is the orbital diagram for hydrogen. It shows the most likely location for the one electron that hydrogen has. Okay? Good there? Okay. If you flip it over to the top of the next page, it asks you to draw an orbital diagram for helium. So, if an orbital diagram is a picture that shows the location of electrons, we need to know how many electrons we have to place on this diagram. So we go to our periodic table, we find helium. We find out that helium has how many electrons? 2. Right? Helium's atomic number is 2, and therefore it has 2 electrons. So, we just found out that for hydrogen, the lowest energy orbital is which orbital? What's the orbital where electrons have the lowest energy? 1s. That's the same case for helium as well. So we draw a line, we label it 1s to represent that orbital. We know that it can hold this electron because from hydrogen. But we learned yesterday that each orbital can hold how many electrons total? 2, right? We refer to that idea that each orbital can hold 2 electrons as the Pauli exclusion principle. Right? Each orbital can hold a maximum of 2 electrons. Yesterday, we represented that idea with the spin quantum number. Right? That sound familiar from yesterday? Yeah. We said the spin quantum number only has 2 values. It's either plus 1/2 or negative 1/2, right? Because we can only fit 2 electrons. So we have to distinguish this electron from the next electron, right? This 1s orbital is not full. It can hold another electron. But it's got to be different than this electron. We represent that with another arrow, but that arrow points downward instead of upward. Okay? Feels good. That's fine. Yeah, if you draw a 2-sided arrow instead of 1-sided arrow, that's fine. Just as long as you show 1 up, 1 down if we have them there. Jafar, go ahead. Well, let's keep going with it. Okay? This is Jafar. This is very much a pattern day. So once we get the pattern down, you'll see that it just rolls. Okay? Okay. Devin, good. So, Devlin asked, what if there's more than 2 electrons? So, the next thing that you come across on your outline, Devlin, is what? Lithium. Okay. Oh. Lithium. All right. So, if we're drawing an orbital diagram, we need to know how many electrons. We look on the periodic table, and we find that lithium has 3 electrons. Yes?
Yes.
Okay. So, first orbital that gets filled is always which orbital? 1s. Why? Because where is it on this where is it on this chart?
Closest to the nucleus.
Closest to the nucleus and closest to the bottom of this chart, right? So, we go back to our orbital diagram. Like we said, we draw a line to represent the orbital. We label it with the orbital name. So 1s is the lowest energy orbital. How many electrons can that orbital hold? 2. We represent that as 1 up and 1 down. Okay? But, okay, so next, this is the lowest energy orbital. It gets filled first. Now it's full. So where are electrons going to go next? The second lowest energy orbital. Lauren looked on her chart. I wanted to give you a shout out on the video because you were yelling in the back of the room, right? So Lauren looked on her chart. She went here. She started from the bottom, 1s. The next orbital that we come across is what? 2s, right? It's the next one that's closest to the bottom. So, we come back here. We represent orbitals with lines. So we add another line, and we label this one as 2s. And then how many electrons will it have?
1 arrow going downward.
Doesn't matter.
No.
When there's only 1 electron in that orbital, just like yesterday with the spin quantum number, if there's only 1 electron, does it matter if it's plus 1/2 or minus 1/2? Not really. So here, if there's only 1 electron, the up and down only distinguishes this electron from that electron, right? But if there's only 1, does it really matter?
No, not really.
Not really. Usually, just by convention, we'll draw it upward, but either one is correct. Okay? Okay, good.
Does it matter which side the
Like the line here? No, it really doesn't. If you wanted, if you wanted to do it that way, that's fine. So as long as you distinguish up from down, and like we said before, if you want to draw it this way with 2-sided arrows, that's cool too. As long as you distinguish one way from the other way. No, that's yeah. Okay. All right. Jafar, question, go ahead. Or did I answer your question?
For the 2s.
Yep.
How many things?
Well,
How many arrows go there?
let's go this. The next one that's on your outline, Jafar, is what? Boron. All right. So we go to boron on the periodic table, and we find that boron has how many electrons? 5. All right. So the first orbital that gets filled is always which orbital? 1s. So line 1s, right? Jafar. Every orbital, regardless of what name it has or what number it has, can hold how many electrons? 2. So 1 up, 1 down. Okay? We filled this one, so we go back to our chart and we find that the next lowest energy orbital is 2s. Right? So we come back here. There's another line, 2s. Right? Jafar, how many electrons can this orbital hold? 2. 1 arrow up, 1 arrow down. Okay? No. So let's go back to our chart, right? So we find here 1s is the closest to the bottom, 2s is next. The next one we come across is 2p. Even though it's in the next column, it's still the next closest to the bottom. But here's where it gets a little different, okay? How many 2p orbitals are there? There are 3. Remember, one on the x-axis, one on the y-axis, one on the z-axis. And on the chart, how many lines are there next to the 2p? 3 to represent each of those orbitals. Now, the very first thing that we wrote down in this outline was what? Or lowest energy to highest energy. And we call that the what? The off-bow principle. Now, if you look at those 2p orbitals on the chart, right? What are you seeing about all 3 of them? They're all the same. They're all the same distance from the bottom. Meaning that electrons that are in these 2p orbitals would all have the same energy. They don't need to be distinguished, or Pat, first, they actually can't. Sorry, not Pat. Devlin, sorry.
It's okay.
My bad. Sorry, Devlin. I apologize. Meaning that they can't be distinguished from each other, but that also means that when we go here on our orbital diagram, we can't say whether an electron would go in this one, or this one first. Meaning that when we're doing orbital diagrams, when we come across the p sublevel, right, we have to draw all 3 of them because they are all the same energy. They are all options. Yes, Pat?
So, like, going back to that, graph thing.
The chart?
Yeah, the chart.
Yep.
So when we're filling out, like there's like the 1s and all that
Yep.
stuff, we just go to, like the next.
Yeah. As far as using this chart is concerned, we start at the bottom and go up. And that's...
No matter which.
Yep, and that's what we're going to do throughout the course of today and tomorrow is get increasingly more difficult, more complex. Okay? So, going back to this orbital diagram, right? How many electrons do we still have to place here? 1. Because we've already placed 4, and we got to place 5. Where does it go? It doesn't matter. These 3 orbitals are all the same energy. So you could technically put that last electron in any one of these 3 spots. What else could you do? You could go up or it could go down. Really doesn't matter. Usually by convention, we're going to fill in left to right just because that's the way we read and stuff like that. But, you know, that's the way we read English, right? We go from there. Okay? Good there? Yeah. Ryan, go ahead.
Say if there are 6 electrons.
Hold on 1 second to that question, all right? Actually, if you look on your outline, Ryan, what's the next element that we have to draw an orbital diagram for?
Carbon.
Carbon. And if you go to carbon, Ryan, what's carbon's atomic number? 6. Funny you should ask that question, all right? But let's go back to this one first, and let's get all the questions answered about this. Jafar, go ahead. If you don't put the last 2 p's with nothing there, will you get it wrong? Yes. Because these 3 orbitals are all the same energy, so we need to write them even though there may not be any electrons in there. Okay? Because they come as a group. They are a sublevel together, the 3 of them. Jules, go ahead. Oh, it's the first P sublevel, okay? So on your outline, when we get to boron, that brings us to the first P sublevel, okay? And when sublevels are drawn, all orbitals within that sublevel must be drawn, okay? There. So helium's orbital diagram represented for us the Pauli exclusion principle. Each orbital can only contain 2 electrons, these electrons are distinguished each from one another. Yesterday, I know you weren't here yesterday, but yesterday we talked about the spin quantum number. We said that those electrons have opposite spin, even though they're not technically spinning, okay? But we represent that with one arrow up and one arrow down. Opposite spin. Did you write down spin quantum number? Somebody did before. I just wondered if you guys said. Okay. But yeah, you can go opposite spin there, right? Okay. Yes, Devlin.
I have a question about the 3
Yeah.
when
Question about the 3 2Ps. Go.
when we get to when we do 6,
Yep.
do we put 2 arrows on 1, 2?
That's where we're going next. So, okay. All right. Good there. So Devlin asked, when we get to an atom that has 6 electrons, okay, like this carbon. So we start off. First orbital that gets filled is always what?
1s.
1s. And that can hold how many electrons?
Those.
1, 2. The next orbital that we come across is
2s.
oh, wrong color. 2s. It can hold how many electrons? 2. Okay. Then, Devlin, the next set of orbitals that we came across were the 2p, and we talked about that there are 3 2p orbitals. Okay. And Ryan, this is where we got your question as well. Okay. So, all together, how many electrons can that set of orbitals hold? 6 total, okay? However, we talked about what do electrons look to do to each other? Repel each other. So number 5 is going to go here. Even though this orbital can technically hold another electron, will the 6th electron go there with it?
No.
No, it wants to stay away from it. Where will it go? A different one. Does it matter which one? No, but it's somewhere different. We refer to this, let me just finish this part up. We refer to this as Hund's rule. So Hund's rule states that electrons are going to spread out as much as they can before they start pairing up. No homework tonight. We will finish this up tomorrow and get into electron configurations.